Hi, good morning everyone. This is Mr. M from Algebra Lessons. In this video, I'm trying to share some information about exponential function with some examples. Exponential functions are functions that you can see really in your real world situations. Knowingly or unknowingly, you are using this situation. See, the current situation is kind of a pandemic called COVID. So the viruses are expanding or multiplying rapidly. So that situation we can use, or we can model that particular situation using the exponential function. Mathematically, we will call that as an exponential function. That growth we will name as an exponential model or an exponential growth. So we can go deeper into this. What is this? How we can model this? Or what are the terms? What are the terms represent? What are the functions? Or how it is behaving? How the graph behaving? So those are the information I'm trying to discuss with you, or I'm trying to share with you in this video. So guys, usually the exponential functions we are actually using in engineering field, biology, economics, psychology, and other fields. We are using actually in high rate. This function is having a high demand for predictions. Okay, if you are trying to study about the population, if you are trying to predict the final outcome of a particular production, or the final outcome of a particular kind of actions, we can use this method called exponential functions, and we can go deeper into this. Okay, if we have a function, if that is growing rapidly, or if it is having an exponential growth, we can represent that function using y equal to a b to the power x. Okay, y is equal to a b to the power x. Okay, what is this a, what is this b, and what is this x? That is the important question that I also had when I started study this exponential function. Okay, so before go further, that means into the very deep side of this exponential function, let me explain in advance what is this a. A represents the initial value. While I'm explaining the examples, you will get an idea what is this initial value. And b represents the growth or decay rate. So this is very important. You should have this very basic idea when you are approaching this. And there are some conditions that these terms should follow. Okay, a should be a non-zero number. A cannot be zero. And this b should be a positive real number. And b cannot be 1. That is very important. Okay, if b is 1, the exponential, we will lose the exponential nature. 1 to the power, whatever it may be, it is 1. So it is actually losing its exponential nature. So specifically the condition b not equal to 1, and b should be a positive real number. That means b can take the value, it is 0. So 0 less than b less than 1. So b can satisfy this condition, and b cannot be 1, and b can be greater than 1. So b can take all these values. Okay, so these are the information you should have before you approach this function called exponential function. Or if you don't have that information, see, this is the best time to study this. So what is b? B is the growth or decay rate. Say for example, decay represents if you are watching the daily economic growth rate or decay rate, you can see that some companies share value is going down kind of a rocket speed. Okay, so we can model that situation using this exponential function, but it will not be an exponential growth, it will be an exponential decay. Okay, so we can go further into this. If depends on this the value of b, we can change the name of the function. So if b is positive, that is if b is not positive, if b is greater than 1, specifically greater than 1, we would say this function grows at a rate proportional to its size. That means this will be an exponential growth function. Okay, so if you can see a function which is having the value b greater than 1, so we can say that is an exponential growth function. So then what will happen if b is less than 1? So b cannot be 1, so b is less than 1. That means we can choose the value 0 less than b less than 1. So that time, see, b less than 1 but not 0, that means some kind of a fraction. So that will be that functions definitely will be a function with a decay, or we will call it as a function with exponential decay. So this is the very basic information we should have when we are reaching this point to study exponential function. Now when we are studying a function, we will study about the domain and range. Okay, what will be the domain, what will be the domain, and what will be the range? So because we are studying a function, the very basic nature of a function is it should have a domain and it should have a range. Okay, so I can explain that domain and range in the actually in the form of a property. Okay, so domain and range. The domain of the function will be always negative infinity to positive infinity. So this, you can understand this if I can draw the graph of this function. The graph, let me try to draw a proper line. Okay, guys, the graph interesting. The graph of an exponential function behaves like this. Okay, so this point is very important. Always the graph of an exponential function in the form of y is equal to ab raised to x will pass through this point 0, 1. And another thing is, see, this graph, this line, this curve is trying to reach or trying to intersect the x-axis, but you know, this line, this curve will not touch the x-axis, and that x-axis will stay as a fence. We will call that x-axis at this point as an asymptote. Okay, don't forget that name, asymptote. Okay, so asymptote, x is the asymptote. Okay, so here the range, see, it is not going below 0, and it is staying, it is not touching, it is not converging to 0. It is showing like, okay, it will touch 0, no, in infinity also it will not. So see, towards the negative infinity it is going, and to the upper infinity it's also going, like for the x value. So the domain is negative infinity and plus infinity, and the range is 0, 0, infinity. You know that because see, the x value is increasing towards right and left, and the y value is not going down to 0. It can converge to 0, but see, that is the asymptotic nature. So it is not intersecting, it is not crossing the x-axis. So we can assume the maximum possible value it can reach is 0. So the range is, the left bound is 0 and the right boundary is infinity. It is going up, the y value, it can take the y value to the maximum extent. And it is intersecting at this point 1 always. So we will call the y-intercept of this function is always 1. See, this is the very basic idea you can keep in mind for kind of an exam called SAT or ACT or any kind of competitive exams. So now I'm going to explain this exponential function with the help of some examples. So examples in the sense, how can we model a situation using an exponential function? Very basic things. If you know the very basic things, you can easily model a situation using an exponential function, or model an exponential function in a situation. Okay, so I said y is equal to a b raised to x is the general form of an exponential function. A represents the initial value and b represents the growth factor or the decay factor. Okay, let me explain a situation. Wait a moment, I need more space. Okay, I can start with a very common situation. Say for example, I have two companies, company A and company B. Okay, company A and company B is planning to expand their number of stores. Okay, so company A and company B is having different strategies and they have their own strategists. Okay, company A strategist or the planner said, okay, we can expand our number of stores. Okay, we can choose an initial point. Okay, company A is having 100 stores already. Okay, so initial value, initially 100 stores company A is having, and the strategist said, okay, we can start 50 more every year. Okay, 50 per year. Okay, and at the same time company B is also having a strategist. He said, yeah, we also have 100 stores. Okay, so that's the initial. And company B's strategist is kind of a tactical person. He said, we can increase or expand our company by 50% each year, 50% each year or per year. Okay, so my question is, just pause the video and think about this. Which company will be the leader after 5 years or 10 years? Just pause the video and think about that. Okay, I will explain this situation. Company A is saying that they have initially 100 stores and they are expanding it with 50 per year. So the strategist can model the situation A of x, if x represents the number of stores after A of x represents the number of stores after x years. So company A's strategy we can model with a linear function. F(x) is equal to 100. 100 is the initial number. 100 plus 50x. So A's strategy can be modeled using this equation. A of x is equal to 100 plus 50x. At the same time, we can model B strategy. So B of x will be is equal to, we have a 100 number of stores, so 100 times we can use at this point the very equation that we studied in your elementary sessions or elementary classes, the compound growth formula. That is, we used it for compound interest. So that is A is equal to P into 1 plus R by 100 to the power n. I'll explain how this comes in the coming examples, but just for the sake, just use this. Okay, because this is also a compound, an exponential growth. So 100 is the initial amount, and see, R by 100, R represents the rate. So here it is 50%. So 1 plus 50 by 100 to the power n represents the number of years. Here in place of x, n, we can use x. So that is 100 times 1 plus 0.5 to the power x. So this is 100 times 1.5 to the power x. So b of x is equal to 100 into 1.5 to the power x. Okay, at this point you can check, okay, which company will be the leader after 10 years. So how you can find it? Just replace. Okay, what you need to do is replace both the case, replace x with 10, because we are actually looking for 10 years. So x is equal to 10 in both the equations. So that will guide you, or that will give you an information about company A and company B. So after the calculation, you can see that company B is leading the situation, or company B is going to lead the situation after 10 years. So that is actually the effect of an exponential function in actual sense. Okay, so I actually need to give you more examples on this particular case, or in this particular function. Okay, the first example I would like to give you is this. Okay, number 1. If x and 1 by 27 is a solution of the equation, this is kind of a basic question in this part called exponential function. This will be useful for your competitive exams or regular class test or something like that. You can use this, practice this in this way. So x and 1 by 27 is a solution of the equation y equal to 9 to the power x, then find x. That is the question. Okay, you can use the previous knowledge that you earned at this point. Okay, so the equation, so the solution we can start like this: y equal to 9 to the power x, and we actually need to find x. Yeah, so then we need to think like this. Okay, we need to find x. We have the equation and we have a point. Okay, and that point represents, point in the sense we the kind of a coordinate. That coordinate represents the solution of this equation. That is very important. That term is very important, the solution. Okay, if that is the solution, we need to find the value of x that satisfies the equation. Okay, we need to find the value of x that satisfies the equation y is equal to 9 to the power x, satisfies the equation 9 to the power x, that is 9 to the power x is equal to, what is the y value, corresponding y value given in this solution, that is 1 over 27. Just pause the video and think about how we can solve this using your previous knowledge. Okay, I can explain this. So Actually, in many cases we can solve this problem using the rule of exponents or by inspection. Yeah, we can do that, but sometimes that strategy may not work. So we can use another strategy by making the same base. Okay, so 9 to the power x is equal to 1 over 27. Let me use a different color. Okay, 1 over 27. So see, we can see that both are 9 and 27 is the multiple of 3, so we can make that in the form of 3. So this is 3 square to the power x, and this is 1 over 3 to the power 3. So this is 3 to the power 2x is equal to 1 over 3 to the power 3. You can write as 3 to the power negative 3. Interesting, guys. At this point, I just want to introduce a property of exponential functions. So if we have two exponential function, b raised to x and b raised to y, and if it is saying b raised to x is equal to b raised to y, then we can say that x is equal to y. This is actually the property of an exponential function. So if the bases are same, then its exponents will also be same. So we can use that property here. Okay, 3 raised to 2x is equal to 3 to the power negative 3. So we can rewrite, or we can conclude that situation as 2x is equal to negative 3. So x is equal to negative 3 by 2. So this is the solution of this particular problem. So you can find the solution of these kind of problems using the same strategy by making the same base for that function. Okay, I need more space to give you more examples, because I'm trying to cover most of the areas that you can expect in a particular examination. So another question I would like to share with you is, let me try to use a different color. Okay, this time this color. Question number 2. Okay, find the base of an exponential function y is equal to b raised to x that contains the point negative 1/3 and 1/4. This is kind of an interesting question. Probably this will be a very easy question. Okay, so we can use some strategy that we used in the previous problem here too. Okay, so we have the function here that is y is equal to b to the power x, and it is given that contains the point negative 1/3 and 1/4. Okay, we have actually the required information. Actually our job is to find the base. Base means this part, that is b. Okay, so because we have the function and the point it contains, we can replace the variable with those points. So what is y? Y is 1/4. Y is 1/4. So 1/4 is equal to b to the power negative 1/3. Interesting. How can we solve it? Think about this. Which previous knowledge helped at this point? We can solve this using the changing power strategy. Okay, we can use squaring technique, cubing technique. Okay, changing power strategy. Okay, here the power contains the variable is negative 1/3. So how can we make that power a unity or a 1? That is the thing that you need to think at this point. Okay, negative 1/3 can make to 1 by multiplying a negative 3 here. So 3 cancel, negative 1 together makes positive 1. So what you need to do is raise both sides of the equation to the reciprocal of negative 1/3. Okay, negative 3 is actually the reciprocal of what? reciprocal of negative 1/3. Okay, so what I'm going to do is I'm going to do that process on both sides. So that is negative 1/4 to the power negative 3, that is equal to this to the power negative 3 is b. So b is equal to 1/4 to the power negative 3. So when you are simplifying this, b will be is equal to 1/4 you can write as 4 to the power minus 1 to the power minus 3. So this is 4 to the power 3 because negative times negative is positive. So the answer is 64 is equal to b. So guys, I believe that explains well. I have a few more problems to explain with you or share with you at this point to understand more about this exponential function. Okay, one more problem. Okay, that is question number 3. Okay, a company purchases a machine for $3,000. Okay, the value of the machine depreciates at a rate of 10% each year. That's a lot. Our objective is to find, or our question is to find or model an exponential rule for this situation for more prediction. And another question is predict a value. What will be the machine worth? What is the machine worth after 4 years? Worth after. I'm just choosing a random number 4. You can choose whatever the number you need after the rule. So I'm choosing 4 years. Okay. So again, pause the video, start thinking what we need to do or how we can start the problem. Okay, so this is the way you can do this problem. Here the machine depreciates. That is very important. We have the initial value and we have the rate. Okay, so first, as a student, I'm always doing like this, underline the required informations. So here the machine depreciates 10% each year. At the end of a year, the machine worth 90% of the value at which it started growing from the previous year. Okay. So did I miss something when I'm saying that? Okay, this is the thing. Okay, if 10% depreciation is there, the value of this particular machine after a year will be 90% of the previous year. That's what I tried to explain in the first statement. Sorry if I missed something in the first statement. So 90% will be the value. Okay, so how can we model this? We know the general form of an exponential function is y is equal to a b raised to x, and we actually need to find out y. So we are modeling v is equal to a is the initial value, so a is 3000, so 3000, and b to the power x. B means the rate of change. So b is 10% each year. It is depreciation. So usually you can use 1 minus this 10%, that is 0.1, or you can write that second year what will be the worth, that is 90%. Third year again 90% of that. 1, that is 0.9, that is the rate, okay, rate of depreciation. So 3000 times 0.9 to the power x. Basically, this will be the value of this machine, or the machine worth after x years. So that is actually the answer for the first question. And the second question is, what will be the worth after 4 years? So basically what you need to do is, you have to replace this x with 4. That means y is equal to 3000 times 0.9 to the power 4. So that when you are calculating this, you will get an approximate amount of $1,968.30. This will be the amount or the price of this particular machine after this much of depreciation and after 4 years. So that is the answer for that particular problem. I have a few more in my list. Then you can see that you actually cover most of the part of the exponential function section in your class level or in your school. So then you can answer most of the problem that you are going to face in your test. Okay, then we have 2 more problems left. One is, how can we write the exponential model if we have if we don't know the initial value? That means the initial value is unknown. That is the situation. Initial value is unknown. Okay, how can we do this? Let me give you an example. Write an exponential function that passes through the point -2, 6 and 2, 1. So -2, 6 and 2, 1. How can we do this? This is very simple. We don't know the initial value, and we know only 2 points through which the exponential function passing. Very interesting. So we know that the general form is y is equal to a b to the power x. Okay, we have 2 points, -2 and 6. When we are choosing -2 x, that means the x coordinate and the y coordinates, we can replace that here in this equation. So the equation become 6 is equal to a b to the power -2. That's good. From this, what will be a? A will be 6b square, I believe. Yeah. A is equal to, from this equation we can reduce a or find a. A will be 6b square. Interesting equation, 6b square. So if you are choosing the second coordinate, we can rewrite this equation as what is the y value? 1. 1 is equal to a b square. 1 is equal to a b square. So we already know what is a, 6b square. So that is 1 is equal to 6b square times b square. That is 1 is equal to 6b to the power 4. So we actually need to isolate b. So eliminate 6 on both sides. That is b to the power 4 is equal to 1/6. And you know how to find b. Take the 4th root, that is b is equal to 1/6 to the power 1/4. Okay, so that is approximately, the value is approximately 0.6389. So you have b as 0.6389. So now we need a. How can we find that a? You have the equation a b square is equal to 1. So from this, a is equal to 1 by b square. Okay, 1 by b square, that is 1 by 0.6389. So that is approximately equal to 2.4492. So this is the value of A. So that this is the way. If you don't know the initial value, you can write the exponential model. So for the final answer, what you basically need to do is you have to plug these values in this equation. So the equation is y is equal to, what is A? A is 2.4492 times B is 0.6389 to the power x. So this will be the exponential model or the exponential function that will pass through these points -2, 6 and 2, 1. So we have one more question I really need to share with you, that is, if we know the initial value. Already I discussed that. Okay, if we know the initial value, let me explain this with a real world question. So this will be the final question. Okay, so in 2006, 80 DO were introduced into a wildlife refuge. Okay, by 2012, the population grown to 180, and it was growing exponentially. Okay, our objective is to write an exponential function that represents the population of deer over time t. Okay, interesting. How can we start this problem, or how can we approach this problem? We have the starting year, starting number. We have an year that we are considering as a marking point, and we have the number of deer at that point too. So if you are considering 2012 as the final year, the final number of deer at this point is 180. Okay, we can use that information. Okay, so if I were you, I will use the deers, that means the number of deer, and the year will form as a coordinate. Okay, so what is the number of deer in the very first year? That is 80. First year means that's the starting year, so consider it 0. And after some years, starting year is 2006. After that means some years, that means 6 years, it is 2012. So 6 year, what will be the number? 180. Oh, now we have 2 points. Now we know how to do this. Okay, so we can model this. Let n of t represents the function. N of t is equal to a b raised to t. We know the number after t years, that is here it is 6 years, so then that number is 180. 180 is equal to a is the initial number, 80, b to the power t is 6 years, because 2006 to 2012 is 6 years. So we need to isolate b to find the growth rate. So eliminate 80 on both sides. So this is 80 divided by 8, that is 9/4. So 9/4 is equal to b to the power 6. So that is b is equal to 9/4 to the power 1/6. That is approximately equal to 1.5. Interesting. We have b. Okay. just plug it back. So the equation is n of t equal to a is 80, b is 1.5 to the power t, because we are looking for the number of deer after a certain number of years. So guys, this is the final equation, or this is the model that we can use for this particular problem. Guys, I hope you enjoyed this video, and I hope you really followed me for this. And if you really understand me, if you really wish to get more videos like this or more videos on your topics, please don't forget to subscribe my channel, and please don't forget to press the bell icon for these kind of videos. Once I'm uploading these kind of videos, definitely you will get it notified if you press the bell icon. So don't forget to press the bell icon, and don't forget to share these videos, and don't forget to comment your thoughts. Means you can explain this in that way or this way, your ideas. I'll appreciate that if you are commenting. So thank you very much, guys. See you soon with another video. Till that, goodbye.